Hi everyone, thanks for attending this talk. Today I'm going to present our work on LLM-Integrated Declarative Program Analysis, where we combine the ability of traditional program analyzers to perform grounded reasoning with the ability of large language models to perform semantic reasoning. For many years, program analysis tools are used everywhere in software engineering for bug finding, security analysis, large-scale code scanning, and so on. And tools like CodeQL, SemGrep, or Combi are good examples that many developers already use in practice. What makes these tools powerful is that they can reason about the program structure by using representations like abstract syntax tree, control flow graph, data flow graph, and so on. We all know that these tools are powerful and they are very effective at analyzing program structure and answering questions which are only about the syntax of the code. But some other questions need different types of analysis, which sometimes require subjective reasoning or access to external knowledge or some form of human judgments. Let's see some examples. In the domain of software maintenance, for example, a developer may want to know whether his code base has variables with misleading name. Or in the domain of software security, one may want to know whether his code base contains string literals or comments which expose private information, for example, a hard-coded password. Or one may want to know whether this code base contains suspicious URLs. So these kinds of questions are difficult or sometimes impossible to be answered only by using traditional program analyzers. And this gap actually motivated our work. Now some of you may ask why we don't simply use LLMs directly for program analysis. I can just give my code base to an LLM and ask whether it has inappropriately named variables. Yes, of course, LLMs have access to external knowledge and they can do some form of semantic reasoning, but they sometimes hallucinate, they lack a structured view of the code. They do not guarantee the soundness of analysis. Also, they sometimes struggle to scale to millions of lines of code, and their precision drops when the code base becomes large. And finally, we all know that these models are expensive. On the other hand, we have, for example, traditional static analysis tools, which have a structured view of the code, and they guarantee the soundness of analysis, and they provide grounded analysis, basically. But they are limited in doing semantic reasoning. And here, by semantic reasoning, I mean any kind of analysis which goes beyond the syntax and anything which cannot be expressed purely in well-defined rules. OK, so now what if we combine the best aspects of these two worlds? So in this work, we propose SemQL, which is an extension of CodeQL. And the key idea behind it is simple. Instead of replacing a program analyzer with LLM, let's augment declarative program analysis with controlled oracle calls. So here, the declarative analysis framework still performs structural reasoning very precisely and efficiently, and it guides the search space. And only whenever semantic understanding is needed, the analysis can call an external oracle, which is in our case an LLM. So basically, these two components can complement each other. OK, now let me show the problem that we are trying to solve with a simple example. The Java documentation provides some guidelines for naming convention, and one of those guidelines says that method names in Java should start with verbs, and the first letter must be lowercase, and the first letter of each internal word must be capitalized. Now suppose that we want to identify violations of this naming convention in a large code base. Using a static analysis framework like CodeQL, it's relatively straightforward to start with. For those of you who may not be familiar with CodeQL, it is a static analysis framework which converts a code base into a database representation. And it allows us to write SQL-like queries over code. And the results of these queries are returned as tables. For example, this query here outputs the name of all methods whose name do not match a regular expression. And this regex just captures the camel case format. So using this query, we can detect certain violations of this naming convention. But the problem is that the names must also start with verbs. So for example, consider a method named userData. Structurally, it follows the correct camel case format, and the regex would accept it. But it doesn't start with verb. And somehow, this name is misleading, because a name like getUserData, printUserData, or processUserData is more suitable here. So the challenge here is that determining whether a word is actually a verb needs some external knowledge about language. And now the question is that how we can augment this kind of analysis with semantic judgments. And that's exactly the problem that SAMQL is designed to address. So using SAMQL, we can write an alternative query like this, which outputs the name of methods that either do not follow the correct camel case format or they do not start with verbs. Let's look at another example from security domain. Suppose a security analyst wants to identify string literals in a code base which may expose private information or credentials as well as URLs that might be untrustworthy. So with SAMQL, we can express these kinds of analysis very naturally. And here, the conditions inside the LLM query can be even much more detailed. Instead of just having a short phrase which describes a condition, you can have a richer description of, for example, what should be considered untrustworthy here. And this even enables a level of subjective reasoning. So here with a single query, we can combine the ability of CodeQL to find relevant program elements with the ability of language models to reason about their semantic. And from a syntactic point of view, SAMQL is almost identical to CodeQL. The only addition is a new construct, which we call it LLM query. And you can think of it as a binary predicate, which takes two arguments. A CodeQL expression and a string literal, which encodes a condition. And this predicate basically holds for all the values which are bound to this expression E, and that satisfy the condition S. And here, LLM query is just treated like any other formula. So it integrates naturally with the rest of the language. For example, it can be combined with other formulas in the word clause using conjunction, disjunction, or it can appear in negation formulas, and so on. Now let me briefly explain how we evaluate these SAMQL queries. First of all, there are two practical challenges. CodeQL is not open source, so we don't have access to its query plan. And we need to somehow convert these SAMQL queries into equivalent CodeQL queries so we can just use the standard CodeQL engine. And second, as we discussed, LLMs are expensive, so we need to somehow minimize the number of tokens that we submit to the LLM. Now consider this query. Given a program, here all I need to know is that which string literals in this program satisfy the condition C1 and which string literals satisfy the condition C2. If I know this given specific program, I can write an equivalent CodeQL query for this SAMQL query. So here a simple solution is that I can write an intermediate query which outputs all the string literals in a program. I can run it. And I can give all these string tuples to an LLM with two prompts and ask whether each of these strings satisfy the condition C1 or whether each of them satisfies the condition C2. And then given the LLM output, we can write two unary predicate in standard CodeQL. P1 corresponding to the first LLM query and P2 corresponding to the second LLM query. And here P1 holds for all the string literals in the current program which satisfy C1, and P2 holds for all the string literals in the current program which satisfy C2. And then we can just simply replace LLM query calls with these materialized predicate, and it results in a standard CodeQL query, which can be evaluated using CodeQL engine. Here the problem is that this evaluation strategy is not efficient because we pass all the string literals in a program to the LLM. But just let's consider the first part of this query, which says that the string must match the regex and represents an untrustworthy URL. So if I have a string which doesn't match the regex, then I don't even need to ask the LLM whether it represents an untrustworthy URL. So let's see a better query evaluation strategy here. Let's assign propositional variables to each atomic condition in the word clause. And now I can decompose this query into two subqueries. And because the formula in the word clause is disjunction, the result set of the initial query is just simply the union of the result set of these two simpler subqueries And more generally, the formula in the where clause can always be converted into a DNF formula. And this allows us to decompose the original query into smaller subqueries. And the final result set can be obtained by just taking the union over the result set of these smaller subqueries. OK, now let's go back to the previous example. Here, I picked the first subquery. And here in the where clause, I have the conjunction of two literals, Q and R. And here, R is an LLM query. Now, if I just eliminate this literal from the where clause, I would have a weaker query. And the result set of this weaker query is a superset of the result set of this initial subquery. So everything which is here should definitely be there. So I just need to submit these tuples to the LLM and ask whether each of them satisfy the condition C1. And so basically here, this query just outputs all the strings that match this HTTP regex. And roughly speaking, for every subquery, we can just ignore the semantic part, these LLM query literals for evaluation. And we just need to identify which tuple satisfies the syntactic conditions. And we just need to ask the LLM whether each of these cases satisfy the semantic condition. So in this way, we can submit so many fewer tokens to the LLM. And I can do the same thing for the second subquery here. Let's just eliminate the LLM query literal, which is T here. Now I have a weaker subquery. And I can now evaluate this query and submit all these tuples to the LLM. But here, notice that some of the strings are already identified to be in the result set of previous subquery because they satisfy Q and R. So because they are already in the result set, it doesn't matter whether they satisfy T or not. So here we can remove these strings from further Oracle evaluation. And in this way, we even can submit fewer tokens to the LLM. So to wrap up the query evaluation for each subquery, we write an intermediate query by removing these LLM query literals from the conjunctive clause in where. And we also add the negation of the formulas from earlier subqueries to make sure that the tuples which are already identified to be in the result set would be excluded from later Oracle evaluation. And briefly, in our experimental evaluation, we collected a set of analytic questions which need semantic reasoning beyond the syntax, and we designed a set of SEMQL queries to answer these questions given an arbitrary code base. And we evaluated these queries over a sample code base from Spotbox using two evaluation strategies. First, the simple evaluation, which I initially described, and second, this DNF-based query evaluation, which I just mentioned. And based on the results, DNF-based query evaluation submits so many fewer tokens to the LLM, almost 81% fewer tokens. And it also takes significantly less time to complete the query evaluation. We also open source SEMQL, so you can just check out the GitHub repository, and you can write your own queries and run them on any code base that you want. Thank you, and I would be happy to receive any questions.
Thanks for the interesting talk. Have you considered using the LLM, basically once you find things that violate a certain condition, using the LLM to amend the rule set? Because I could imagine that then basically the next time you run it, you would have to call the LLM even less, which would save additional tokens.
You are saying based on the outputs that we have, we remove some parts of the? Yes. I don't have the details here. But yes, that's the case. We also, because like, it's a bit hard to explain, but if you read the algorithm in the paper, you can find this part. Yes, that's correct. So for every tuple, let's say for every tuple and every condition, we only evaluate once that whether this tuple satisfies this condition or not.
Hi. So you are looking at the security applications, right? And then you are using an LLM. Do you do you worry that you will leak sensitive information to the LLM?
It could be one case, but basically here the problem that we have is not like we don't necessarily need to use these, like for example GPT or everything. We can even use our local LLM. So the problem is general. It can be even any kind of external oracle. It doesn't need to be an LLM. So the evaluation strategy and the SAMQL is independent of the oracle type. You can just use a database, for example, or anything. And that's the problem we didn't think about, but yeah, it might be the case that, for example, we have information leakage or something, but you don't necessarily need to use like these general LLMs. You can use your local LLMs, for example.
I can have one question. Oh, question there.
Thanks for the talk. So is this used for mostly syntactic queries, like the list that you have here, for example? Are there sounds like it would be useful only for extracting like literal string-based comparisons from the input program, or do you also have support for things like type checking or context-aware analysis around the code that you can bake into the queries somehow?
Basically, any kind of analysis that you can express in CodeQL can be also used in SAMQL. I don't think that like these type inference and these kinds of things can be done with CodeQL, but basically the problem is that, okay, you have a search space. For example, you want to identify from methods, fields, I don't know, every kind of program elements, and you have some structural conditions. This can be already done by the CodeQL. But now here you also want to identify whether these things satisfy some semantic conditions. So in these cases, we add SAMQL. So for any kind of reasoning that you can do this in CodeQL, you can also use SAMQL. I'm not sure whether these kinds of analysis that you are saying can be done in CodeQL or not, but that's the case.
Okay. Thank you.
Other questions? I have one question. On your slides 11, there's this case in the gray boxes.
Here?
No, 10.
10.
10. Yeah, those cases in your gray boxes.
Right.
Cases. Gray boxes, task cases.
Yeah, the cases are just some string literals from the program. Like this is some example.
So they are strings hard-coded in the program.
Exactly.
What if for different program, they have different hard-coded strings, you will try specific that hard-coded strings in the specific program?
We are doing this given specific program. So for every program, we are doing this query evaluation. So query evaluation can be done for a specific program, and these are the things that we are doing. So for another program, we again repeat this pipeline.
I see. Thank you. Any other questions? Then let's thank Sara for your presentation. And let's welcome Elizabeth again. Sorry, because our program.